Hello, this video will go over section 4.6 of chapter 4, and it's about molecular shape. So we've learned how to do Lewis structures, and Lewis structures gives information about how the atoms are connected, but it implies nothing of the geometry or shape of the molecule. And so to determine the shape around a given atom, first we need to determine how many groups surround the atom. A group is either an atom or a lone pair of electrons. And then we will use the VSEPR theory to determine the shape. VSEPR stands for Valence Shell Electron Pairs Repulsion Theory. And so remember that electrons are negatively charged, and as electrons are negatively charged, they will repel each other because like charges repel each other. So electrons will repel each other, and the most stable arrangement for them is to keep the groups of electrons as far away from each other as possible. And so this will imply and give a certain shape to the molecules, because electrons will try to be as far away from each other as possible. And so we will go over the different shapes that we observe. The first one, when two groups of electrons surround the central atom. So an atom that is surrounded by only two groups is linear. And has a bond angle of 180 degrees. So here you see in the model that the central atom would be the red atom, and then the two blue atoms are surrounding the red atom, and they are exactly opposite each other on either side of the red atom in the middle. A more realistic example with CO2. CO2, you see the Lewis structure of CO2 on the left, and carbon is surrounded by two oxygens, with and it's bonded with those two oxygens with double bonds. And so when we count the number of atoms surrounding carbon, carbon is the central atom in this case, we count that there are two groups around carbon. You count the double bond as one electron group, and the other double bond is another electron group. You can also count just the atoms, and that will lead to the same results. So when you have two groups around the central atom, the geometry of the molecule is linear, and the two oxygens are exactly opposite each other on either side of the carbon. And the bond angle, what we call the bond angle, is the angle between the two bonds, between two consecutive bonds. So when an atom is surrounded by three groups, the molecule will take a trigonal planar shape, and the bond angles will be 120 degrees. So in the model here, where the central atom is the red sphere, it's surrounded by three blue spheres, and they are exactly equidistant from each other. And the bond angle between two consecutive bonds is 120 degrees. And it's the same to the left and for the two atoms under the red atom. So it's called trigonal planar because it's in the shape of a triangle, and it's planar because all atoms are in the same plane. So an example is H2CO, formaldehyde. So the Lewis structure for formaldehyde is shown here with carbon in the center, bonded with two hydrogens and one oxygen. And so the Lewis structure is showing already the shape of the molecule because the bonds are all equidistant from each other, and there is 120 degrees between two bonds. And so all atoms, the two hydrogens, the carbon and the oxygens, are all in the same plane. So it's a flat structure. And so when you count the number of atoms around the central atom here, you count the number of atoms and you see that there are 3 groups. When an atom is surrounded by 3 groups, but one of those groups is a lone pair, then the geometry will be bent. It's bent from trigonal planar, and so the bond angle is still 120 degrees between the 2 bonds. For example, the molecule of SO2 is like that. If you look at the Lewis structure to the left, S is the central atom, and it's surrounded by 3 groups. There is a single bond, that's one group, a double bond, that's another group, and the lone pair, that's the 3rd group. So 3 groups around S will mean that it's going to be trigonal planar as far as the electron group geometry is concerned. But because the lone pair is not visible, because there is no atom there to show that there are electrons on that side, then what you see is really a bent shape with 120 degrees between the 2 bonds. And the reason why the molecule takes on that shape, it's because there is the lone pair, you know, on top of the sulfur there that is not shown, but that repels the other electron groups. So it repels the single bond and the double bond away, and that's why you get a bent shape. When an atom is surrounded by 4 groups, the molecular geometry is tetrahedral, and the bond angles are 109.5 degrees. So a tetrahedron is a structure where you have a central atom and then 4 atoms surrounding that central atom. And all blue atoms there are equidistant from each other. It doesn't matter which way you hold it. If you decide to hold it from another of the blue atoms, it will look the same. When you will use the ChemMagick website to do the lab 3, you will be able to play with those models and see how they look like if you were holding them in your hands. But right now on paper, let's look at the example of methane. So methane, the Lewis structure on the left shows that carbon is surrounded by 4 hydrogens with single bonds. And so that means 4 electron groups around carbon, the central atom. And those 4 electron groups, they will push each other and take on that tetrahedral electron group geometry, where they are all equidistant from each other, the hydrogens, and the angle between 2 bonds is 109.5, and it's the same angle between every 2 consecutive bonds. So it doesn't matter which way you look at it, or as 109.5 between every 2 bonds. And so the next slide will show how we draw this on paper. We use wedges to show that. So let me go over this here. So by convention, when you are asked to draw a tetrahedral shape on paper, you will always represent solid lines for bonds that are in the plane of the paper. So you try to put as many bonds in the plane. And so in the case of a tetrahedron, you can only put 2 bonds in the plane. So the bonds in the planes here are straight lines. Then you will use wedges. A filled wedge represents a bond coming out of the paper toward you. So that's a bond that would be coming towards you. And a dashed wedge represents a bond going behind the paper away from you. And so when you draw these, So you want to give pyramidal shape to the 3 bonds that are going downward. And then one of the bonds that is in the plane is just straight up. What you want to pay attention to is that you put the 3 bonds that are making the base of the tetrahedron. They should be downward. They are not perpendicular to the vertical bond. They are going downward, and you will always draw the 2 wedges on the same side next to each other. And then on the other side, you will draw the single line that shows the other bond in the plane. So let's look at some more molecular shapes. If the 4 electron groups around the central atom include a lone pair, the geometry is trigonal pyramid with bond angles of 109.5 degrees. So a typical example is NH3, ammonia. If you look at the Lewis structure of ammonia to the left, ammonia is, nitrogen is the central atom. It's surrounded by 3 hydrogens with single bonds, and there is a lone pair on the nitrogen. So that means there is 4 electron groups around the nitrogen, the 3 single bonds plus the lone pair. So we have a tetrahedral electron group geometry. However, the lone pair is not visible when you look at the molecule. The lone pair is there and repels the other electron groups and gives the shape to the molecule. However, it's not visible. And so that's why you get this trigonal pyramidal shape where you have a pyramid with a triangular base, but there is no bond going upward from the nitrogen straight up. It's gone because in there it's where is the lone pair, and the lone pair is not bonded to anything, so that's why it's not visible in the shape of the molecule. However, as I said, it's there, so it's repelling the other 3 bonds downward, and that's why they have this shape, trigonal pyramidal shape. And so if you are asked to draw this on paper, it would be drawing the 3 downward bonds. Again, you would use a single straight line on one side to show the bond in the plane. And that's the only bond you can have in the plane with this structure. And on the other side, like here on the right, you would draw the 2 wedges, one filled wedge and one hashed wedge. And these 2 wedges, they show a bond that comes towards you from the plane of the paper. And the other wedge shows the bond that goes away from you behind the paper. So that's how we would draw this. For example, in your lab 3, you will draw them like this. Another molecular shape, if the 4 groups around the central atom include 2 lone pairs, then the geometry is bent from tetrahedral. And so the bond angle is 105 degrees, which means very close to 109.5, but it's a bit misshaped. So the angle is slightly smaller. A typical example of that is water, H2O. If you look at the Lewis structure of water on the left, the oxygen, the central atom, is surrounded by 2 hydrogens with a single bond, and then 2 lone pairs. So there are 4 electron groups around the oxygen, the 2 single bonds or 2 atoms, and the 2 lone pairs. And so you have, as far as electron groups are concerned, you start with a tetrahedral shape. However, this time we have 2 lone pairs, and so 2 atoms that are gone. And so that's why you end up with a bent molecule with an angle of 105 degrees. because the two lone pairs are, not visible. They're there to repair the two bonds, and that's why we have a bent shape. But we don't see them anymore in the final shape of the molecule. So this table is provided in your reference packet for Chem 121. It is important that you have this table on hand. You will need it whenever you are asked to find the shape of a molecule. So it's good to print the reference packet for Chem 121 where this table is provided. So the way you want to read this table, you need to look at the number of electron groups that you count around the central atom. And so see the little asterisk here that says count only electron groups around the central atoms. Each of the following is considered a one electron group: a lone pair, a single bond, a double bond, and a triple bond. It doesn't matter that these are, double or triple bonds, they count as one electron group. So when you know your number of electron groups around the central atom, then you need to determine out of these electron groups how many bonding groups you have, which means how many atoms are surrounding the central atom, and how many lone pairs. And so depending on those numbers, you follow the line to the right, and you will get the electron geometry, the angles between the electron groups, and then the molecular geometry. And so when you're asked about the molecular shape, that's what you want to read. It's molecular geometry. It's what you want to record. Because the electron geometry shows the geometry due to the number of electron groups, but what you see for the final shape of the molecule, it's called the molecular geometry, and that's what you want to look at. And so you have typical examples for each of them. So let's practice this and draw the Lewis structure and then state the number of electron groups, lone pairs, and bonded atoms in each of the following molecules, and then use the VS-EPR theory to determine the shape of the molecules. So I want you to pause the video and work this on your own before you watch for the answer. It is important that you practice. So let's start with PF3. So once you've done the Lewis structure, you should come up with this Lewis structure where P is in the center, surrounded by 3 fluorines. All the fluorines have 3 lone pairs each, and they are single bonded to phosphorus. Phosphorus has a lone pair and 3 single bonds around it. So if you count the number of electron groups around the central atom, here the central atom is phosphorus, and we have 4 electron groups around the phosphorus, 3 bonded atoms, and 1 lone pair. And so you want to look at the table we saw previously and follow the line that says 4 electron groups, 3 bonded atoms, and 1 lone pair. And this will show that it's a trigonal pyramid shape. So here you want to look at the line that starts with 4 electron groups, that has 3 bonding groups, and 1 lone pair. So it's the line before the last. It says the electron geometry is tetrahedral, but the molecular geometry is trigonal pyramidal. So if you draw it using the conventional way that chemists use, that's how PF3 would look like. You have, because it's a trigonal pyramid, you want the 3 bonds to be inclined downward. The 2 edges on the same side next to each other. And then on the other side, the single bond in the plane with a straight line. And they all should look downward and make a pyramid with a triangular base. And to show why we have this shape, you can show the lone pair on the phosphorus, and that really justifies why it takes on that shape. It's because of the lone pair on the phosphorus that those 3 other bonds are pushed downward. Now let's look at H2S. When you have figured out the Lewis structure, you should come up with this Lewis structure where S is in the center, surrounded by 2 hydrogens. The sulfur has also 2 lone pairs. So when we count the number of electron groups around the central atom, sulfur, we get 4 electron groups, 2 bonded atoms, and 2 lone pairs. So let's look at the table. So we said we have 4 electron groups. So you want to look at one of the 3 lines on the bottom of the table. Then we said 2 bonding groups and 2 lone pairs. So it's really the bottom line of the table that has 4 electron groups, 2 bonding groups, 2 lone pairs. It says electron geometry would be tetrahedral, and the molecular geometry is bent. So then it's bent with an angle of 109.5. So H2S is bent from tetrahedral according to the table. And so when you want to draw that, you can draw the 2 bonds in the plane. And so you can draw them as straight lines. You have to bend them, you know, have with an angle of 109.5 or so between the 2 bonds. And then to justify the shape, you can show the 2 lone pairs on the sulfur. And this shows you why this molecule is bent. It's because of those 2 lone pairs pushing the 2 bonds, you know, closer to each other. Because all those electron groups repel each other. So now let's look at CCl4. When you have worked out the Lewis structure, you should come up with this, where carbon is in the center, surrounded by 4 chlorines. All the chlorines have 3 lone pairs each, and they are single bonded to carbon. So when we count the number of electron groups around the carbon, we have 4 electron groups. It's 4 bonded atoms and 0 lone pair. So let's look at the table to see what this suggests. So we said 4 electron groups, 4 bonding groups, 0 lone pair. So it's a line towards the middle of the table here that says 4 electron groups, 4 bonding groups, 0 lone pair. You have an electron geometry that is tetrahedral, and the molecular geometry is also tetrahedral, right? Because there is no lone pairs, so then the electron geometry and the molecular geometry match. So let's go back to So we said we have a tetrahedral geometry for CCl4. So the way to draw the tetrahedral shape is by using the convention of having 2 bonds in the plane, and they are drawn with straight lines. And so that's the vertical bond going up from carbon, and the one going to the right downward. So those 2 lines show bonds in the plane. and then you want to draw the two wedges on the same side, next to each other, like parallel to each other, going downward and to the left in this case. And so that's how you would draw a tetrahedral shape. So let's do some more practice by using the Lewis structures that we found earlier in this chapter. So you already have the Lewis structures provided for you. And so here you need to predict the shape around the central atom. So sometimes you have two central atoms, but you can see that the molecules are symmetrical. So when you decide the shape around one of the central atom, it will be the same for the other central atom. So let's go through CS2. CS2, you have the Lewis structure there. C is surrounded by the two sulfurs and double bonded to each of them. And so when we count the number of electron groups around C, we have two groups, two atoms. So if you look at the table, so in the table, we see two electron groups, two bonding groups, 0 lone pair. That's the first line. And it says that the electron geometry is linear and the molecular geometry is also linear. So CS2 then has a linear shape, right? Because two electron groups, two bonded atoms, 0 lone pair lands to a linear shape. Let's look at C2H4. So here it's an example of a symmetrical molecule with two central atoms. The two carbons here are similar and they are both considered central atoms. So when you want to determine the shape, you need to focus on only one of the carbon. So focus on the carbon on the left, for example, and you will see that it's surrounded by 3 atoms, 2 hydrogens and the other carbon. So that's 3 electron groups, which are 3 bonded atoms. So let's look at the table. So according to the table, when we have 3 electron groups, which are 3 bonding groups, and we have 0 lone pair, so it's the second line. It says we have a trigonal planar electron geometry and also a trigonal planar molecular geometry. So that means the shape around the carbon is trigonal. So the geometry is trigonal planar for each carbon, because if you do it for the carbon to the right, you also see that you have 3 electron groups around it. 2 hydrogens plus the other carbon bonded. So the geometry around both carbons are trigonal planar. Let's look at H3PO4, phosphoric acid. And if we look at the molecular geometry around P, P is surrounded by 4 oxygens with single bonds. And so that's 4 electron groups, 4 bonded groups, 0 lone pair. So let's look at the table. So 4 electron groups, 4 bonding groups, 0 lone pair. So it's the 4th line from the top. It says the electron geometry is tetrahedral and the molecular geometry is tetrahedral. So that means the shape around P is tetrahedral. You could look also at the geometry around the oxygens and focus on an oxygen at a time and also find out the geometry around them. But let's move on to P2H4. P2H4 is a symmetrical molecule, and it has two central atoms, the two phosphorus there. So when you want to determine the shape around one of the phosphorus, focus on that one, and it will be the same for the other phosphorus. So if you focus on the phosphorus on the left, it's bonded to two hydrogen and one phosphorus, the other phosphorus, and it has a lone pair. So that makes 4 electron groups around that P. So now let's look at the table. So we have 4 electron groups and 1 lone pair. So starting from 4 electron groups, 3 bonding groups, 1 lone pair. It's the row before the last. So 4 electron groups, 3 bonding groups, 1 lone pair. The electron geometry is tetrahedral, but the molecular geometry is trigonal pyramidal. So the molecular geometry around one of the P is a trigonal pyramid. But you see that if you would do the same thing with the phosphorus to the right, you would come up also with 4 electron groups, 2 hydrogens plus 1 phosphorus plus the lone pair. So that's 4 electron groups, 3 bonded atoms, 1 lone pair, and that would also come up with a trigonal pyramid shape for that phosphorus.